Yo, what up? Welcome to Made by Ozzy. I'm Ozzy, and on this channel, we're turning this DE0-CV FPGA development kit into both a cryptocurrency miner and a GPU. So on the last episode, what we did is we got the 7-segment displays here. We built a hex decoder so we could actually show hexadecimal numbers on there, 0 through 9 and A through F. Today, what we're going to do is we're going to end up right back in the same spot. What we're going to do is we're going to refactor the code that actually breaks up the hex characters for that using for loops in Verilog and the keyword generate. This is a pretty advanced technique, and I'm only using this hex decoder example as a way to illustrate how to do it. In real world, I probably wouldn't do it for something like this. It's really, there's only 6 of them, and it's actual hardware, so it's never going to change because it's a dedicated board, right? But it's a good sample, a good practice run for how to use for loops and how to use generate, because that's going to be the main way that we instantiate varying instances of cores. Like when we build a crypto miner, we're going to build a core to run the hashing algorithm like SHA-256 or odocrypt or whatever, and we're going to just make as many instances as we could fit on this chip. That's how crypto works. We're just going to define the algorithm and just try and do as much of it as we can. Same thing with graphics. We're going to build our own little processors basically to compute vertex shaders and fragment shaders, and then to get good performance, you just fill up the chip with as many of those little processor cores as you can. So learning how to instantiate without having to hard code in all of the instances is very key. So let's get started. Okay, so here I got the Cordis project Copper opened up, and last time we made this module here, this Hex Decoder Rev B, with 6 different inputs and 6 different outputs. And here's the verilog for that module, where we created instances of this core module, and we just hard coded in 6 different instances. So let's take a look at what we're going to do to make this a little bit more general. Okay, so this is what we got right now. What we're taking is this much bigger bus, the local 42-bit counter, and we're feeding in 4 bits at a time, 6 different inputs, 1, 2, 3, 4, 5, 6. And on the other end, we're getting 6 different outputs, 1, 2, 3, 4, 5, 6, of 7 bits long. And this is what our module is doing on the inside. It's feeding into the input named hex in 0, 4 bits into the core, and that core spits out a 7-bit output here, and we just do it 6 times. So what if we didn't want to have to manually type in or specify all of this input and this output? We actually had to specify all of those in our Verilog code. So what if we just wanted to feed in all of the same bits from the local 42-bit counter, bits 41 down to 18, and populate the same displays out here? What if we could format our module here? We'll make a rev c so that the input vector here is actually going to be of size n times 4, because we know we have 4 bits, and our n will be the number of displays, which in this case is 6, right? So if we have n inputs, then we're going to need a vector that's n times 4 long, and 41 to 18, this is 6 times 4 is 24 bits. We're going to need an output that's n times 7 long, because we have 6 displays, but each one needs 7 bits, so this would be a 42-bit vector out. And we need an instance of this module, the Hex Decoder Core module, for every single display that we have. And so let's go see how we're gonna do this. Okay, so here we go back in Cordis. Let's create a new module, new Verilog HDL file. Okay, let's give it a name, module, and this is gonna be rev c, or next attempt at it, rev c, and then the inputs need the same clock and reset. And then instead of having all of these 6 different inputs and 6 different outputs, I'm actually only going to define one input, so hex vector in, call it that, and we're going to have one output, display vector out. Okay, go ahead and add the keyword end module here. I'm going to go ahead and hit save here and give it a name. Okay, so let's put it in library, and Hex Decoder Rev C. Okay. Okay, before we specify our inputs and outputs, we're going to do a little bit of math to actually use a variable number of displays to determine how big these two, this input and this output, how big those vectors should be. So we're going to introduce this keyword, local param, and we're going to give it a name. So num displays, and we're going to assign this to 6. So before I mentioned FPGAs only have 2 data types, registers and wires, and so that's still true. I'm introducing this new thing, local param, but what makes the local param different is this is a number that will never be synthesized. This is a number which will only exist right now during compilation time. So it has to be known when we compile, and all of the effects of it, well, we're going to use its effects to actually generate the code. So that's something to take away. A wire and a register are actually used by the FPGA while it's running. Local param is used purely at compile time, and then doesn't actually, it affects what gets put onto the FPGA, but it doesn't affect the logic itself, if that makes sense. And we'll see. So we're going to display a couple other ones. These will be useful. So we're going to want hex bus width equals 4, and this will, because we're going to, each hex number needs 4 bits, and one more. Local param display bus width equals 7, because we need 7 bits for each 7 segment display. So now what do we want? We actually need to know the length of these 2 vectors here. So we know that hex vector in is going to be for 6 displays. Each display needs 4 bits. So let's make another local param. Local param hex vec length, and we're just going to multiply these 2 numbers. Num displays times hex bus width. Great. And let's do the same thing for the length of this other one. We'll call it display vec length, and that's also number of displays, times display bus width. All right, great. Now we could specify our I/O. Well, I guess I could have specified clock and reset before. They're just 1 bit, they don't care. But this other one, input. Okay, so we know it's going to be 41 to 0, but this number hex vec length should be 6 times 4, should be 24. Oh, I said 41. We know it's going to be 23 to 0. So what we could do is take this number, hex vec length, and subtract 1. And that goes all the way to 0. That's not gonna differ. And this is hex vector in. Great. Now do the same thing for output, and of course we're going to use this different vector length that we calculated. This one should be 41. Display vector out. Great. All right, we got our I/O all set up. Save. Okay, next step is what I need to do is create an array so that I can take this longer vector and look at the individual bus widths that I actually care about. So what I'm going to do is specify a new wire. I'm going to declare the bus width. So I'm just going to do this with the hard constant so we could see it first. And let's just call this hex array. And so this here specified that it's a bus width of, it's 4 bits from 3 to 0. And now I need to tell it basically how big is the array, the size of the array. And it's going to be 6 elements long, and you specify it sort of in the same way that you specified as bus width, just backwards. Instead of 0 to 5, or instead of 5 to 0, you do 0 to 5, and this tells me, or this tells the compiler that I want 6 elements of this. My array has, each element of the array is a 4-bit bus, and I have 6 of those elements, and that equals 24 bits total. And I'm going to be able to map the 24 bits of this hex vector in to this array, hex array. So I'll be able to actually look at each bus, each 4-bit bus, by specifying an element or an index of this hex array. But this is, hard constants, so let's go ahead and replace these with our local parameters that we specified up there. So that's 4, so I got to subtract 1, and then num displays for the number of elements there. Okay, and let's make one more for the display array. And the bus width is different, but the number of displays is the same. They are both arrays are 6 elements long, but their overall number of bits will differ because each element of the array is now a different bus width. Okay, save. Okay, let me add some comments, keep it a little clean while we're at it. Preliminary math. Okay. Define inputs and outputs. Declare local wires. Okay. Next thing we're going to do is generate instances. So, believe it or not, the keyword here is generate, and associated keyword and generate. Okay, and we're going to use these to actually automatically create this local parameter num displays number worked of this hex decoder core instance. So what do? So we're actually going to need a for loop, and in order to use a for loop, we actually need to specify one thing outside of this generate block. We need to specify a variable name we're going to use for the for loop, which is just I. We're going to use for I. So you specify a for loop in very much the same way you do in other language in C++, for I equals 0, I less than some number. In this case, it's going to be this number, num displays. And then there's no I++, so you have to actually type the whole formula, I equals I plus 1. And what's a little bit different, we still have the begin and end syntax for a for loop. But when you specify a for loop inside of a generate block, you actually have to give it a name. So so this for loop needs to have a name. And let's name it make core, right? Okay, that's a good enough name. It could be any name, any string is fine. Okay, so now inside this for loop, we have access to this variable I, and we could use that to do things. So what do we want to do? We want to create the instances. Let me label this. Create instances, and we need instances of this module, Hex Decoder Core. And we need to give it an instance name. So before we hard-coded instance 0, instance 1, instance 2. In our case here, the for loop is going to automatically append a 0, 1, 2, depending on the I. We don't need to do anything except specify a root string, and we'll just call it instance here. So I'm going to copy all the same I/O we had from this one and tab it in so it's clean. Okay. So clock and reset remain unchanged. Data in is now, it's not going to be hex in 0. We don't have a variable named hex in 0, and this is not going to be display 0. We don't have a variable for that. What we do have is this here, hex array, and we could look at index I of hex array, and we're going to map that into this instance. And then we're going to do the same thing for display array. Okay, cool. That should do it. Okay, let's see if we can make a file, a symbol out of this, and that'll tell us if we actually, for logic makes sense. And unfortunately, I forgot, I actually cannot create a symbol file for verilog modules which have bus widths for actual inputs and outputs that are variables. This is, it's actually not a verilog consequence. It's something specifically to when I try to create a symbol, for specifically for, Chorus's schematic thing. So it's not a verilog thing. This is actually okay syntax still. I just can't use it as a symbol in a schematic diagram like this. The compiler is immediately going to catch whenever I try and specify a bus width using a variable length. So I am going to, in the future, we'll have instances where we will actually declare the bus width as variable like that. But in this case, just for the sake of teaching and clarity, I'm going to go ahead and hard code these in so I could actually make a symbol and use it. Okay, that did it. Okay, so I just checked the logic, but I'm actually not done here. I need to add this comment, and that's what I need to do. I actually, you may have noticed that I created this array, this hex array, and then I used it down here, and then I created this display array and I used it down here. But you may have noticed I never did anything to tell Verilog that this hex array has anything to do with this input hex vector in. And the same thing for the output, display array, display vector out. So this is where we get into something called packing and unpacking arrays, where I sort of create I guess it's a map really from this vector in to this array, hex array. So when you pack, or when you go from long vector to an array, it's called unpacking the array. So what we're actually going to do, it's a wire, right? So we're going to use the assign keyword, and what we're going to do is going to assign hex array each element. Well, first thing you got to do actually is I got to create a whole other for loop for what I'm about to do. So for I equals 0, it's all under the same conditions. In general practice, I'm not gonna lie, this is actually one thing I'm not 100% sure why it doesn't work well, but when you're gonna create a mapping like I'm about to, it's best to have it in its own for loop and not inside the same for loop that's doing the logic, but we'll get back to that. So it's from I equals 0 all the way to less than num displays. So num displays is 6, this will go to 5. I equals I plus 1. And again, we have the begin and end syntax. For I, make core, name it that, because we need to give this one a name as well. And I'm just going to name it unpack. For I unpack. And now we're going to use the assign keyword, and what we're going to assign hex array element I, and it's going to be equal to. Okay, so we actually need to figure out an index in this longer vector, hex vector in, to assign to this here. And what we can do is go ahead and create another local param right here inside this for loop, and we're gonna call it I guess index start would work just fine. Okay, and what is this going to be equal to? Well, so we want to do, you know, the first 4 bits would be 23, 22, 21, 20. So we want this to start at 23 for I equals 0. So what we can do is take advantage of, we calculated the length of the vector. So we have this local parameter, which should be 24. So probably minus 1. And then as I increases, we want it to go down by 4, which is the bus width here. So we're going to do minus I times the bus width. Alright, and this should do it. So hex vec length is going to be 24 minus 1. That'll give me the 23 that I actually want. And then as for I equals 0, this will be 23. For I equals 1, this will be 23 minus 4, so that'll be 19. That's good, that's what I want. So that's what I want. And now I need to tell it, look at the vector, hex vector in, and start looking at index start. And normally you could do something like this, index start minus 4 or something. Actually, minus 4 plus 1 is what it would be. But there's actually a little neat trick. This minus colon, and then you could specify how wide, you want a bus of X many bits. Instead of specifying the start and end bits to actually look at, you can specify just the start bit to look at, and then a bus width. And it will actually look at the right bits for you. This is perfectly valid syntax, and we'll be using it a lot. Okay, so we've went ahead and unpacked. We created this map from the bigger vector, hex vector into our local vector, hex array, or local array. Perfect. Now we actually need to do one more to tie the output, this display array to display vector out. Okay, so let's come down here. We'll make another one. And you know what? I should note that I'm putting the second one, the output after just create instances. It actually doesn't matter. I could have put them both up at the top. Because this is parallel programming, the order of things matters less so than data types and everything. It's all happening in parallel, so it doesn't matter where I specify this in Verilog. It's all going to happen at the same time anyway. So let's make another for loop. For I equals 0, I less than num displays, I equals I plus 1, begin end, and I'll just name this one pack. A little comment for pack. All right, good. And I'm gonna need something similar to this. So local param index start, and I could reuse the same name here, index start, and that's because much like C++, there's a scope for local parameters. So if I declare one inside of this for loop right here, or inside of this begin and end block, then these other ones can't see it. That local param does not exist for this for loop nor for this for loop. So I could reuse the names without worrying about conflicting or whatever. It's fine. So in a similar fashion, I'm going to start with, instead of hex vec length, I'll use display vector length, subtract 1, and then subtract I times, and this one has a different bus width, not hex bus width. It's going to be display bus width 7. But otherwise the formula is the same. Okay, and assign is going to work backwards this time. Instead of assigning to the array, we're actually going to assign to the vector from the array. So we're going to take this vector and we're going to start at this index start that we calculated. We're going to use this handy little notation, minus colon, and specify the bus width. Okay. And now what are we going to assign it? We're going to assign it the array index value of display array, the ith index. Okay. That's good. That should do it. Let's see if this can make a symbol. Good to go. All right. Okay, so let's drop that into our top level here. And it should be in project. That's where it gets added. You may have noticed that I cleaned out some of the other ones. I did that before this video started here. But okay. So let's take. I'm gonna cannibalize everything from this module over here. Steal that clock and reset. Actually, before I steal it, let me leave it there. Make a copy. Maybe I won't steal it. Maybe I'll just show that I can comment it out by just getting rid of this here and leaving everything else there. But okay, so what's our input going to be? Our hex vector in. Before I was using all these bits of local 42-bit counter, and I'm going to use those exact same bits because I want to get to this basically, right? So I'm going to use bits 41 to 18. So local 42-bit counter, 41 down to 18. All right, great. Now this other side though, I need to do something else, don't I? Because I actually cannot combine these 6 outputs into one long vector. I have 6 different outputs. Unfortunately, I'm going to end up having to build another little thing to break it out into 6 things. And that's, it's only because it's physically tied to an output. I'm mostly doing this to show you guys how you can use parameters to, make things very variable and easy to adapt. But in this specific case, because I'm so close to the physical output, I need to make something to sort of fan this out. Okay, so let's make a new verilog module, new verilog HDL file. And this one's just called module, how about we call it unmap displays. Yeah. And what we're going to have is vector in, that's the long vector, and we're going to have our 6 displays out. 4 and display 5. That's 6. All right, add keyword and module. Okay, and now I just need to map it. So I'm going to use a neat little trick here, the same sort of thing that we did in the other ones with some local params. I'm just going to declare this one, bus width equals 7. I know that. And so what can I do actually is I could use that to sort of make it easy when I assign which bits from vector in get assigned out to display 0. So these are wires, so I'm gonna use the assign keyword, display 0, the entire bus width, right? Equals vector in, and let's see, I need 41, 41 minus down to bus width. Okay, now but for the next one, this is where I could use this trick. Oh, I forgot the 0 up there. So display 0, display 1, 6, colon 0. And so what I can do is do on this side 41 minus bus width. And what I'm going to do to show how easy it is times 1. So I'm going to go up here and actually add this same thing to right there and just show it's times 0. And I could add this same little. Okay, now it's much easier to copy and paste. 3, 4, 5, 6. Okay, display 2, 3, 4, 5, and I just need to change these here. 2, 3, 4, 5. Okay. Yeah, in hindsight, actually, I didn't need this bus width here, but whatever. Okay, this should work, and I should go ahead and be able to save this. Give it a name. Unmap displays. Okay, and let's see if I can create a symbol out of it. Copper.bdf has been modified. Yeah, because I added that symbol over there. Oh, okay. Oh, well, I forgot to display my inputs and outputs. What a dunce. Input. The size is going to be 41 to 0. It's a 42-bit vector. Vector in. And output, they're all going to be 6 to 0, 7-bit vectors. Display 0, display 1, display 2, display 3, display 4, display 5. Okay, that should do it. Let's see if I didn't mess up again. All right, successful. Okay, so let's go ahead and drop this new symbol into our schematic diagram here, unmap displays. And so I should be able to just take, well, let me line it up here. Yeah, take this, map it directly into there. All right, great. And I should be able to just steal all the outputs from this. So highlight them all, Control X to cut, Control V to copy, and then just line them up. Okay, looks good. Let's hit save. All right, great. Now let's see if this compiles. All right, compilation successful. So let's actually try this out on our board. So tools, programmer, and go ahead and write it out. Let's see if that worked. Okay, cool. So we have all the same, functionality, which is what we expected. So we were able to successfully refactor the code and not break everything. That's always great news. Great, so we know that worked. All right. And so one of the big benefits that you may be able to take away from this is now look at these parameters we have to play with that we could just easily change. You know, if we had 600 displays, we would have to change very minimal amount of well, that's all. We wouldn't have to change anything else in our code except for this right here. And that, again, that is only because of my, because I wanted to use it as a symbol in this schematic diagram file. If I was implementing this module inside of another verilog module, then I could have left it with a variable bus length. There's nothing wrong with that in verilog. It's only because of this schematic type symbol in Quartus. So yeah, that's something to take away, is the actual how valuable being able to address things with parameters like this are. Okay, and notice I didn't change anything, but it went ahead and told me everything is out of sync now because I hit save. Something else I want to point out too is notice 75 ALMs. We're actually, this is equivalent code. We've literally made code. This here is the exact same logic modules as this here. So that's an important takeaway. Because, one thing when I was first doing this, I was like, well, I'm adding this extra wire array. Clearly, I must be using some extra logic modules. But really, this is just in place to sort of guide everything through it. It's no different than, how I define the arrays here. Mind you, I didn't end up, or I say arrays, but the inputs and outputs, which are all wires here. Mind you, I do have a wire, this input is a wire, and I specify another wire. But a wire connecting to a wire, sometimes we'll just synthesize to make one wire. So effectively, I added no logic to the actual FPGA fabric, but I was able to make it so it's easier for me to change the verilog code by using those parameters. Okay, we have successfully used generate and for loops in our project Copper to instantiate varying instances of some core module in Verilog that we wrote. Copper reviewed all the work. He said it was all good to go, so we're good to go. All right, and you know, you could always download the whole GitHub and get right back up to sync whenever, if you haven't been coding along with yourself. All the source code is there. If you've been following the videos, you have, you know, a nice little bag of code to pull from whenever you need to, you know, incorporate it in some other project you're working on. But I hope you're following along, because this stuff is cool, right? On the next episode, what we're going to do is we're going to build ourselves a way to communicate to the FPGA from some software which we write on the PC, like in Python or in C++ or something. And what we're going to do for that, we're not going to use this little USB port on the FPGA. That would actually, we'd have to incorporate a USB to JTAG. It's like a ASIC and FPGA specific type of communication protocol. We're not going to do that. We're going to do what is quite possibly the easiest communication protocol that exists, RS-232, or you may have heard it referred to as just UART, which is UART, Universal Asynchronous Receiver Transmitter, or some people just call it serial. Sometimes I'll just call it serial when I tell people about it. And what we're going to do is actually just add in some of the general purpose I/O pins on this dev kit, and we're going to use RS-232. There's a couple other tools that I need to do that. I need this USB to RS-232 adapter, because RS-232 has this, let's see if I get it in the camera, this little 9-pin connector, which most computers don't have anymore. My laptop doesn't have that. It only has, you know, 2 USB ports, so I need this little adapter. And then we need this other little guy. This is called a level shifter. We need to make sure that the voltages between the voltages used for this communication channel are gonna actually work, and that they're not gonna fry my chip. FPGAs are notoriously really low voltage signals. This one I believe is 3.3 volts. And you may know that USB on a computer is 5 volts. So all this does is it lets me shift the voltage from 5 volts down to 3.3 volts. And, you know, this stuff, I got this off of MasterCard, and I got this off of SparkFun, and I got the wires off of Amazon. Everything's pretty cheap and easy. And I'm adding it all to madebyozzy.com if you want to go get links there. I really wish I could have got some Amazon affiliate ads for it or something, but, you know, it's just SparkFun. I couldn't, and McMaster. Okay, so thank you for joining me. I hope I get to see you guys next time. Take care. And just a reminder that I do have madebyozzy.com if you want to go see some more reference material on sort of, we're going to do RS-232 in the next video, so you can get some information on it before I actually release the video. You can see there's some things there's the link to get the USB to RS-232 adapter. Here's the level shifter off of SparkFun. You can see there's some things I need to add to do share software, to do share Verilog, and I should probably have this up before the next video is out. So if you want to go take a look at it, there it is there. And then there's actually some references if you want to get started on learning a bit about crypto mining on FPGAs as well. So in addition to having the whole GitHub repo link, you could get the whole repo and the user manual for the DE0CV. There's these 2 really good blog posts which have really helped me. In this one, Reverse Engineering the Antminer. This guy actually rips apart an old ASIC Bitcoin miner and actually figures out the communication protocol, like the actual messages that get sent back and forth. This post is a legend. And this one here, Bitcoin mining the hard way. This guy gives the best details about the actual data that you need to process to mine Bitcoins. And I recommend reading both of these as preliminary reading. I will go over the key information out of both of these, but they're good reads. And if you're interested in this stuff, I highly recommend taking a gander at these 2 blog posts. And then, of course, if you like this content and you feel like helping me out, I have all my crypto receive addresses here. So, thanks for watching.